Okay, so you've heard about the Cray XC30 architecture, the Cascade, as we used to call it. That's the important stuff about how the interconnect works, what the node is, the programming environment. So I'm just going to briefly talk about the configuration of Piz Daint, the actual machine that we have here. So that was the artist's impression, and you'll be able to see, if you haven't already, the actual machine in the machine room. The largest system in the world, as I like to say, 12 cabinets. The only other machines at the moment are 4-cabinet systems. So what exactly do we have? Well, 12 cabinets each with 192 compute or service nodes. There are actually 188 in each one, with then a service blade, 188 compute nodes. So there's 2,256 in total, 36,000 cores, 72 terabytes of memory. Peak performance just sneaks in at 750 teraflops. I think it's something like 750.3 or something along those lines. If you'd taken one more core out, it wouldn't work. So there are 5 ES login nodes, and I'll talk about those briefly in a moment. Each one with two Sandy Bridge sockets and 256 gigabytes of memory. Then there's a Cray Connection that Nathan talked about, Connection 1600 for the Scratch file system. And we also have a little test system of our own, but you don't really need to know too much about that, apart from we're in good hands because we have the exact duplication, some Connection and some ES login. So the current way for anybody who's got access to Rosa that we have the system set up looks like this. Well, it doesn't really, but this is my way of thinking about it. So we have a set of compute nodes with a big high-speed interconnect, and on Rosa you then have these service nodes. And as a user, you would log into Ayla, and then you would do your compilations and so on Ayla, and then you might submit your batch jobs. But sometimes you might actually have to even log into Rosa itself. And you're actually on the machine. The Scratch system, you're effectively, well, it's an NFS mount, but effectively going through here to get to the Scratch storage system. This has worked very well, but there are some limitations. For example, in the ability to transfer data around between different systems. So the change for Piz Daint is that we've gone and bought some more equipment from Cray than we did in previous years, where we'd done some things ourselves. So we have directly bought from Cray that Scratch file system based out of Connections. And it sits effectively, therefore, outside of the Cray machine itself, and it's just a Scratch file system. And therefore, if the machine is down, if Piz Daint's down, it doesn't matter. The file system is still there. It's an appliance. It's on its own. And that means that, therefore, also, because it's a Lustre appliance, we can plug other pieces of equipment into it to be able to get fast access. The other thing we have is the login nodes. Now, one thing that's happening with Ayla is now about 4 years old. It's getting a little bit old in the tooth. It's still perfectly functional and still perfectly good for connecting to the outside world. But we didn't want to have to get a second Ayla or play around too much. So what we're doing, and we're doing this with Rosa as well, is Ayla is no longer going to have a programming environment on it for you to actually do those compilations, etc. Instead, Ayla will just revert to being the way you get into our center. This is very good for the system administrators and so on. It means that they can spend all their time making sure that this is fully secure. Anything that's slightly wrong with this, that's where they're going to concentrate their efforts. That's the only way in for external users. And then, from Ayla, you jump over onto an ES login node, which is a very powerful node to be able to do that compilation that you might previously have done on Ayla. And it saves us not having to use things within Piz Daint itself. It also means that we can have many fewer service nodes on Piz Daint by having them the external nodes, and if we need to reprovision, if we find we don't have enough of these login nodes, we can just get some more, and we don't have to touch the main machine. So this is very good because the fewer service nodes we have, the more compute nodes we have. And we all like compute nodes because they allow us to do some science. So these ES login nodes, we also have internal login nodes on Piz Daint that we do need for one or two very specific purposes. But most sites that are getting XC30 systems are not really doing anything in terms of having login nodes allowing you to directly log into the system. And over time, it may be as well within a year or two with some changes to the software stack that we don't need even that as well. So Piz Daint has 5 of these external ES login nodes for accessing the system. If you just SSH Daint, then you will be popped onto one of these ES login nodes. The same thing will transition, just I'll mention this, on Rosa in about a month or so's time. If you SSH Rosa, you will end up on login nodes external to the machine itself. But if you log in, you will be on these login nodes. If you need to get onto the internal login nodes, you need to ask for specific nodes. You know you're on one of these external login nodes because it's Daint 101, 102, 103, and the other ones don't have that one. There's 0, 1, 0, 2. These should be used for all your compilation, your performance analysis and batch submission, job monitoring, and for transferring data. Okay, so I'll mention the file systems shortly, but when you've got to transfer data around from place to place, these are the nodes where we're going to be having fast access to all the file systems. The other reason we want this to be the big data transfer place is if we happen to have, for some reason, some instability in a file system or something goes wrong, by having it on these nodes, if one of these nodes has a little bit of a problem, it's much safer for us in that the main computer can carry on, people's science can continue, we don't have jobs getting crashed and so on and so forth. The internal login should therefore only be used in some special circumstances, and particularly if you need an interactive batch session. Sometimes you do need to get onto an internal node to be able to be directly there where your app run line runs. Now, all of these nodes use the same processor. Now, this is important for anybody who's been on Rosa in the past. You will have perhaps noticed that the nodes you were compiling on, be on Ayla, be on the Rosa login node, was a different processor to the one sitting out on the compute nodes. This had 2 effects depending on which way you looked at things. One was if you tried to compile something for the compute nodes and you'd loaded the programming environment, and then you tried running on the compute node, you'd often get illegal instruction. It just wouldn't work. More important one for our perspective, because you saw that and it crashed and it's fine. The more important one would be if you compiled on the compute node, on the login node, and you were trying to build something, etc., and you hadn't got the right flags, you wouldn't perhaps be optimized for the compute node out there because you'd be trying to target the host, which didn't have the same vectorization capabilities, etc. With Rosa, we're doing the same thing as we're doing here with Daint as well, and that is we're moving to nodes for the login, which are the same as the compute nodes. So therefore, none of this stuff should happen in the future. But from day one here on Daint, we're just using the same nodes. The other thing is the ES login nodes have direct mounts of all the file systems that are of importance for transferring data around, and particularly for /scratch to make sure you get good, fast speed. You should be able to transfer your files at gigabytes per second. So let's compare these nodes. So the ES login, the login, and the compute all have the same processor. It's even the same clock speed. It's a 2.6 gigahertz, 8-core Sandy Bridge processor, official name E52670. There are other differences that you would notice if you're on an internal versus an external login node. The internal login nodes, because they have some extra space for some PCI Express equipment so they can see the outside world, actually only have one Sandy Bridge processor. They also have much less memory. This is significant in that what we're trying to achieve here is that you've got plenty of capacity for compilations, for doing data analysis, etc. So these external login nodes have 256 gigabytes each, whereas if you're on the internal, you'll be a little bit compressed. and we have 5 of these. We only have 3 of the internal nodes, and that number may decrease as well if we don't find that we've got a particular use for them. File system availability is the next thing that's of significance here. So the thing you should notice here from the ES login is that there's availability of all of these file systems that are important to our users. Store should be coming soon. But the others have got fast access, so you can get fast access to the /scratch file system. The GPFS native mount makes sure you get fast access to the project file system where you'd store your large amounts of data that you want to be relatively persistent, and the smaller user and apps file systems. As we move further away from the ES login nodes, things change for the file system. So the first thing is lack of availability of store at all, and a weaker mount on those internal login nodes. This is all to encourage you to not use them as much as possible. You should need to use them as little as possible anyway, but the weaker the mount, the less likely you're going to try and do something on there. It also applies, though, this login is not just talking about login, but is also talking about the node where your app run command actually runs. In that if you've therefore submitted a batch script, we don't want you spending your time transferring data around in your batch script and wasting compute resource while you do so. So we're encouraging you instead to do the transfers before you even begin. And when you get out onto the compute nodes, then what we're saying to you is, this is the file system you should be using, /scratch. Now we've always said this, but then we mounted every other file system that we had on there, so people would start to run out of project and maybe out of their home directories and so on. And here we're making a positive decision that we want you to be using that Scratch file system. So there's some availability of users and apps. You can use users and apps for where your executable lies, for example, or maybe there's some read-only piece of information sitting around somewhere that's of use to you. But we don't really want you using that, and certainly don't want you writing to it. And at the moment, it's mounted read-write, but it may be that in the next few weeks there's a decision to even turn that into a read-only mount, so that you can get your executable, but that's really all you should be doing with this file system. So the take-home message from that is use Scratch. Do all your data transfers on the ES logins, and then only use the Scratch on the compute nodes. One of the other things is, as was mentioned before, by having fewer file systems mounted in a weaker fashion over here, if there's a problem somewhere else in the data center where maybe there's a file system that would possibly take down machines, if we have as few mounts as possible over here, there's less likely to impact there. And so stability is something we're very concerned about at the moment with this very big machine. So that's our system. That's what the ES login nodes look like, etc. So I'm just going to briefly repeat something that Nathan was talking about, and that is for people coming from the XE, the difference between the Sandy Bridge and Interlagos nodes. They appear very similar, although, as you mentioned, sometimes different things such as the operating system and such as compilers might actually see the Interlagos as 32 cores and the Sandy Bridge as 16, etc. But for some cases, they appear very similar. But the first and most important thing that you will notice from your applications as you move forward is point 1. The Interlagos is actually not just two dies, not 2 NUMA domains. Instead, it's actually 4 NUMA domains hidden underneath the covers. The Sandy Bridge is 2 real NUMA domains. Much more importantly as well, they've actually done a very, very good job of making it so that if you do cross NUMA boundaries in terms of memory accesses, it's nowhere near as much of a problem as it was on the Interlagos. Then you've got the fact that those compute units, well, actually they're 2 separate little cores in there, but they share the floating point resources, and that causes all sorts of problems when we're trying to optimize and work out what to do. And for example, therefore, we have, when we were doing our annual or biannual calls for proposals, we'd ask people to say, what's your peak performance? It's spit out by a Cray tool, CrayPat, and it was reporting what was half the performance that was actually there, because even there was confusion. Well, do we say that you're using the AVX per core? Well, you can't if everybody's running on it. So there was a little bit of an issue there. It's a great confusion. Here, instead, the opposite mentality is going along. We say we've got 16 cores. You can use hyperthreading, but the default is to take the opposite view, is to say, well, no, we're taking it as one unit, and it's up to you to split it down if you wish. So, just to finish off then to say about the programming environment on this system. It's similar to Monte Rosa, but there are some small changes. The most significant one is the PGI compiler being missing. So Cray have this approach of saying you can have third-party compilers, and it may be that for some of these things, such as PGI, they might provide you with an MPI library or a minimal infrastructure for you to be able to get away with. This then puts the burden on compiling HDF5 and NetCDF and FFT libraries and all the rest, and trying to get them optimized. And we no longer, therefore, can rely on Cray doing a good job in that area. So even if PGI becomes available, as far as in terms of an infrastructure to surround it, on this system, in its current form, we're unlikely to be offering it, unless there's 500 users screaming for it or whatever. There are also some weaknesses even further than that, as things stand at the moment, for other compilers. So the official 2 compilers that Cray have been saying for the last year are the ones to use on an XC30 system are the Cray compiler itself and GNU. And Intel has been sitting there in this interim stage, as it isn't it, or whatever. Well, most people are expecting Intel compiler to be available on a machine with Intel processors. And so what actually also is there is that for the scientific libraries, libsi is not available at the moment for Intel. Now, there is a little bit of a push around for people saying that maybe they would like Cray's scientific libraries for the Intel compiler as well. And if it's something that's of importance to you, you have to tell us so we can tell them that they have to do it. Or they wouldn't probably listen to us, but there is a community of other sites who have a similar approach. Everything else is very similar. Module framework is very similar. CrayPat for the performance tools and so on and so forth. The Cray Reveal tool we've been using ourselves and is something that we find quite useful and we'll try and encourage people to use as we need to move to things such as OpenMP and maybe in the future OpenACC scoping. Slurm, as mentioned before, and we have DDT debugger. There's a one day after this course on the DDT debugger. So, where do we stand at the moment? Well, we had this thing delivered and installed in December 2012. It's currently undergoing that testing phase, the hardening phase, and it's now in pretty good shape. There's a few lingering bugs and little issues that we need to work out, but it's almost ready for general user access. Production project access, therefore, is going to be on the 2nd of April. So anybody who's got a production project and received a letter from Maria Grazia saying you have time on the system, that's when it will begin. It should be the 1st of April, but nobody's coming in on the 1st of April. It's a holiday. So, sorry? Everywhere. Exactly. Easter Monday just happens to be Easter Monday and All Fool's Day and the day that our allocation scheme starts. Okay, so you've heard about the Cray XC30 architecture, the Cascade, as we used to call it. That's the important stuff about how the interconnect works, what the node is, the programming environment. So I'm just going to briefly talk about the configuration of Piz Daint, the actual machine that we have here. So that was the artist's impression, and you'll be able to see, if you haven't already, the actual machine in the machine room. The largest system in the world, as I like to say, 12 cabinets. The only other machines at the moment are 4-cabinet systems. So what exactly do we have? Well, 12 cabinets each with 192 compute or service nodes. There are actually 188 in each one, with then a service blade, 188 compute nodes. So there's 2,256 in total, 36,000 cores, 72 terabytes of memory. Peak performance just sneaks in at 750 teraflops. I think it's something like 750.3. Then there's the Cray Connection that Nathan talked about, Connection 1600 for the Scratch file system. And we also have a little test system of our own, but you don't really need to know too much about that, apart from we're in good hands because we have the exact duplication, some Connection and some ES login, or something along those lines. If you'd taken one more core out, it wouldn't work. So there are 5 ES login nodes, and I'll talk about those briefly in a moment. Each one with Sandy Bridge, 2 Sandy Bridge sockets and 256 gigabytes of memory.